We continue our introduction to Racket by learning about Racket lists. This will go quickly because Racket lists work a lot like ML's lists. In particular, the way we used ML lists in section 1, where we used functions to access the pieces of a list. So let me just go over the primitives and then I'll write some examples. And again, because it works a lot like in ML, I expect this will not be too surprising. In fact, it'll be reassuring to see some of the same ideas in a different language. The way we write the empty list is with the word null. In ML, we would have written bracket, bracket. The empty list, we write null. It's fine. By the way, if you have seen scheme, this is different. In scheme, you often wrote it parenthesis, parenthesis. That will not work in Racket. We will use null to write the empty list. If you want to build a list, use the function cons. It won't surprise us that in Racket, that's going to come first before the two arguments, just like plus comes before the arguments to plus. This is what in ML we wrote with colon, colon between the two arguments. So cons will take an element in a list and create a list one element longer. If you have a list and you want to get the head, use this built-in function char. And if you want to get the tail, use this built-in function cdr, spelled CDR, pronounced cdr. This is what in ML was the head function HD and the tail function TL. And finally, to see if a list is empty or not, we can use null question mark, which we often just pronounce null, or if you prefer, null, huh? And this is what in ML was the null function, null. So perhaps a little confusing that we write the empty list, null, and ask if a list is empty with the null question mark function, but every language has its different names for things. Just a couple more things on the slide that you see here. If you wanted to build a long list, you don't have to say cons of 3, of cons of 4, of cons of 5. There's a provided function list that takes a bunch of arguments and makes a list out of those arguments. So if you pass it n expressions, it evaluates those n expressions and then makes a list of length n. We had similar built-in, in fact, syntactic sugar in ML for when we wanted to do this. And finally, I should talk about these names char and cdr. Why on earth would you have the function for accessing the first part of a list be called char and the rest of the list cdr? Don't try to figure this out in terms of English. It's a historical accident going back several decades and sort of the original machines that this sort of language was implemented on. These things should not be called this, but it's too late. We're stuck with them. OK. So that's everything we need, but it will make a lot more sense after we just write a few functions, simple things like we're used to. So let's first write a function. I have a comment here, sum all the numbers in a list. OK? So remember, I could define a variable sum and then lambda take in a list x's. I prefer instead the syntactic sugar version of doing exactly the same thing. So I added that parenthesis and then the arguments. This is a one-argument function. And now at this point, we're very comfortable with a recursive solution to this function. If the list is empty, so I'm calling the null question mark function with my argument, then 0. That's the second argument to if. The third argument to if will be a function call the function plus, with the result of calling the function char on x's, i.e. the head of the list, with calling sum recursively with the cdr of the list. OK, so that's the end of the call to cdr, the end of the call to sum, the end of the call to plus, the end of the if, and the end of the define. If you're not used to languages like this, you might find it funny that I ended with so many parentheses. It's incredibly natural. You get used to it. It's exactly that I have to finish all these calls, and then I have a perfectly good syntactic function. And I could go ahead and run this and try sum of, how about the list with 3 and 4 and 5 and 6, and I would get 18. OK? No problem. By the way, just while we're talking, we'll talk about this much, much more. But if you do something like this, this would quote unquote compile, because there's no type checker to stop us, but we'll get an error. And Dr. Racket even tries to tell us where this error occurred in the code. And it says that plus expects a number, and you gave it a string high. OK? So that's our first example of a list function. Let's do a couple more. You know my favorite, which is append. It turns out append is built into Racket. We could shadow it, but I find shadowing confusing. So how about I call it my append, taking in two lists, x's and y's. By the way, in the previous segment and this one, you'll notice I sometimes have hyphens in my variable names or here in my function name. That's perfectly allowed in Racket. It's just a syntactic thing to get used to. In many languages, we prefer to write it like this or like this. All of these work. It's just a bit more of the convention in Racket to separate the words of our variables and function names with a hyphen. Every language is entitled to its own conventions. OK. MyAppend is a function that takes two lists, x's and y's. If x's is empty, return y's. Otherwise, cons the first element of x's onto the result of appending the rest of x's onto y's. It was beautiful in ML. It's beautiful in Racket. Let me show you those close parentheses again. Finish the recursive call to MyAppend, the call to cons, the conditional, and the define. This will work great. Okay, so that's append. And let's do one more. How about map? So that we see something with a higher order function. Works just fine. Again, this one is built in, so how about I call it myMap? Map, as in ML, takes in two arguments, f and x's. Remember, in Racket, this is really a two-argument function, so this isn't tupling or currying. And we know how map should work. It should apply f to every element of x's and return a list of the same length with the result of those calls. So if you have a length 0 list, you end up with null, right? So I asked here, is x's null? If it is, I want to return the empty list. I could have written x's here, but I wanted to show using the null value. Okay, the variable null is essentially bound to the empty list. Otherwise, cons f of car of x's. All right, so what have I done so far? I got the head of the list, and I called f on that head of the list, with that head of the list. So that's my first argument to cons. And then my second argument to cons, I can hit return here if I want it to indent nicely, is to call map recursively with the same f and the rest of the list. And the call to cdr, call to mymap, the call to cons, the if, and the define. Okay, so that's map. And we can run all this. And we'll see if we do that I do now have a function myAppend. The REPL will say that's a procedure, the same way ML like to say that's a function. I'm not going to print anything else out for you. MyMap is also a procedure. If I try to call MyMap with just one argument, like lambda x plus x1, this will be an error. And that's because MyMap expects two arguments. But OK, let's go ahead and call MyMap with two arguments. In fact, let's define a variable foo to be the result of calling MyMap with this little anonymous function plus x and 1. So what I've written just here, you see highlighted in the gray, is just an anonymous function. Takes in one argument, x, that it's in its own parentheses. And the function body is a call to plus with x and 1. And then for my second argument to MyMap, how about I cons 3 onto consing 4 onto consing 5 onto null. Of course, I could have used the list function to write this more concisely, but I want you to get used to lots of parentheses. This is not hard to read. That's the list containing 3, 4, and 5. Close the call to MyMap. Close the call to define. Hit return. That worked just fine. The REPL doesn't tell us anything. It was happy to do that definition. But if I ask it to evaluate foo, it will tell me that that is the list 4, 5, 6. The way the REPL prints lists is with this quote and then the list elements. And that's fine. That really is the list cons 4 onto cons 5 onto cons 6 onto null. And we'll see that because if I evaluate this, I will get the same thing printed by the REPL. So that's our practice with list functions. Again, they work a lot like in ML. They're just as convenient and powerful. Recursion is just as useful.